Okay, so I work on antibiotic resistance, specifically looking at how fast are we working towards getting treatments for the so-called superbugs. So we all know how we got into this mess that we're in with antibiotic resistance. There are so many theories on how we got into this, but one of the most prominent idea is that we had a whole period of time where we're not producing any new antibiotics, so our wells were dry. But at the same time, the bacteria were developing new resistant mechanisms that we hadn't witnessed before. So in this whole 35 years when we didn't have new antibiotics, bacteria had enough time to develop all sorts of resistance mechanisms. And because of that, we're in a position where right now we don't have enough antibiotics to cater for all the different types of resistance mechanisms that are there in bacteria at the moment. So the particular class of antibiotics I look at are beta-lactams. They include penicillins, and there's such a long history of Oxford and penicillin. But they, at the moment, are about 43, depending on where in the world, they're about 43% of the administered antibiotics. And there's been a lot of resistant mechanisms developed towards beta-lactam antibiotics, and in many cases they are no longer effective. So what these antibiotics do, basically, they're workers on the bacterial cell wall that work towards and ensuring that you have a rigid cell membrane that makes sure you don't get you can control what comes in and out of the bacterial cell. And penicillin basically attacks the workers that make sure that this cell wall is, the integrity of this cell wall is maintained. So when they attack the workers, then things get in and out of the cell unnecessarily, and so the bacteria dies. So one of the most prominent ways of resistance to beta-lactam antibiotics is secreting these drones, so to speak, that attack the antibiotics and break it apart before it can get to its active site. And so in that, when bacteria produce these enzymes or warriors, so to speak, they are capable of existing even in high concentrations of the antibiotic. So what my work basically does is looking at these warrior enzymes, looking at how are they produced in the cell, how are they transported from the nucleus to the active site, which is the periplasmic space. How do they fold properly there, and how can we be able to look at how they've evolved over the years? And in so doing, we might be able to develop chemical compounds that we can send in together with the antibiotic that will go attack the warriors and go on and allow the antibiotic to go on and do its job. I could essentially stop there, but the point is really identifying these beta-lactamases, the warriors in the cell, being able to characterize them, understand how they work and how they fold and how they evolve, and then using that information develop chemical compounds that can inhibit these beta-lactamases that cause resistance. So one of the things that I've been working on for most part of my first year was developing chemical probes to be able to identify bacteria that are producing beta-lactam breaking down enzymes. So what you do is you get a compound that looks like an antibiotic, but on the side it's attached to a probe that changes color when it's broken down by the beta-lactamases. So you can be able to check for the presence of these enzymes both in a lab environment for high throughput screening, and you can also be able to use this for diagnostic purposes. So the idea is the compound actually goes in and fits into the active site of the enzyme, is broken apart, and you have a color change. So you have a change from a clear solution to a bright yellow solution because of the paranitrophenol ion that is attached to the compound. So what we're doing at the moment is developing more potent compounds like this that have a fluorescent group. Instead of a changing in color, you have a change in fluorescence, so they're a bit more sensitive. And at the moment, we're trying to test them at Queen Mary University London to see if they can be applied in a clinical setting. So the other thing is basically looking at characterizing these enzymes. Like when I started, this is NDM1, it's one of the superbugs. When I started, we had only 2-3 variants of this enzyme. By the time I was in my second year, we had 8, and now we have up to 16. So trying to understand why are they changing. In many cases, they change only one amino acid to another one. And some of the questions that have been raised by this is, are these changes actually changing the resistant profile? And if so, how? Are they changing it by increasing the catalytic activity so that they can be able to chop up a lot more antibiotics? Or are they changing their own cells so that they can be able to exist in harsher conditions when you have infections, or harsher conditions when you have antibiotics present? And the other question is, what does this really mean for inhibitor development? Are we going to produce an inhibitor today and the next 2 months it can no longer be used? So I started this work in my second year, and the thing that we've been looking at is one of them was activity. We looked at activity of purified enzymes out of the cell, and then looked at how they look like in the cell. So one of the interesting things is that there was actually quite a big difference. So the later generation variants, the ones that came out like in the past 2 years, in the plate, they didn't, in our lab environment, they didn't seem to have such a huge difference in activity compared to the earlier generation ones. But when you put these things in the cell, there's actually a really big difference. The later generation ones seem to have increased activity towards meropenem and imipenem, and these are two carbapenems antibiotics that are used in multi-drug resistance infections. So we're wondering what exactly is going on in the cell that is making them a lot more effective there than they are outside the cell. So what I did was look at the secondary structure, how do they fold? We did this by crystallography, so crystallizing the protein and comparing how they fold, how the different proteins fold, and then we also did it in solution to just see how do their secondary structure look like. And what we saw is that they basically just look exactly the same, so they're not really changing, or the later generation ones are not really changing how they fold, because that would be an energy consuming process in the cell and it wouldn't want to go down that road. So the other alternative is how stable are these enzymes, how different is their stability. And so what we found out is that in many cases, the later generation ones are a lot more stable by about 10 degrees Celsius, so they would be stable in very high temperatures compared to the earlier generation ones, meaning that they were probably evolving to be able to exist in infectious conditions where the temperatures are higher than in the normal cellular conditions. So this is also published work, and we're trying to do this with other classes of beta-lactamases to see if actually this is reproducible for all the other evolutionary trends for other beta-lactamases. And so finally, I work also on inhibitor development, because with all the information that we have about beta-lactamases, the next important thing is to find something that we can block these enzymes with so that the antibiotic can go on and do its work. And these are some of the compounds that we've been able to identify. We've tried to see how they bind inside the active site by crystallography. So we get the compound and stick it inside an enzyme and see exactly which are the parts of the enzyme that interact with these compounds. And in so doing, we can modify it so that it can be a better binder and it can efficiently knock out these enzymes. So basically that's it. Identify the enzymes, characterize them so you can be able to know how they look like and how they fold and how stable they are, and find ways of inhibiting them. So yeah, thanks to my people that I work with. And basically, we cannot fight resistance. We can only make sure that we remain a step ahead, or at least delay it long enough to be able to produce new antibiotics.